Hello and welcome to the Group 8 project presentation. I am Parvati Sonia Suraj. I am a graduate student at the Department of Chemistry and Chemical Biology. My fellow group members are Jordan Foster, Finlay Haynes, and Diego Bernal. Regarding Rutherford backscattering spectroscopy, some aspects of the historical background can be looked into. This technique was named after Ernest Rutherford, a physicist who came to be known as the father of nuclear physics. He won the Nobel Prize in Chemistry in 1908 for his findings related to the radioactive substances. RBS is a unique technique as it does not use reference standards and is used to characterize thin films. Giger-Marchant experiment and the theoretical understanding of alpha scattering forms the fundamentals of this backscattering technique. RBS is a non-destructive surface analysis technique which is used to determine the composition, thickness, and depth of the sample. A schematic representation of the working of RBS is shown here. Three main components are used for the instrumentation: a helium ion source, linear or tandem particle accelerator, a detector which measures the backscattered ions and is positioned at a backscattered angle with respect to the incident beam. Usually, silicon surface barrier detectors are used. Nowadays, tandem particle accelerators are used to achieve higher acceleration with lower voltages. Here, the ion source emits negatively charged helium ions, which pass through the positive terminal located at the center of the tandem accelerator tube. Initially, the negative ion is accelerated from the ground to the terminal. At the terminal, the ions pass through a stripper material, mostly made of carbon foil, and the excess electrons are stripped from the ions, thereby converting the helium negative ions into positive helium ions. The positive ions are further accelerated towards the ground due to the Coulombic repulsion from the positive terminal. This generates highly accelerated helium 2+ ions of approximately 2.25 mega electron volt and is directed perpendicular to the sample specimen. During collision, energy is transferred from incident particle to the target sample. Particles that are backscattered by the surface atoms of the sample is detected by the detector. The backscattered electrons generate electronic signals which is amplified and processed by digital electronics, and the output is displayed as an RBS spectrum. Backscattering can occur only if the target atom has heavier mass than the incident ion. In short, Rutherford backscattering involves an elastic collision between the projectile, which is a high energy particle from the incident beam, and the target, which is in the sample. The picture of an accelerator is shown here. Accelerators are instruments which are used to accelerate charged particles to very high velocities. A schematic representation of the Rutherford backscattering is shown here. Next, what does the analysis tell us? Mass determination can be done by a kinematic factor. The energy of the backscattered helium ions are dictated by the conservation of energy and momentum between the incident ion and the scattering atom and can be related to the depth and mass of the target. Since Rutherford scattering cross-section of each element is known, quantitative analysis of atomic composition can be determined from the RBS spectrum obtained for film less than 1 micrometer thick. Determination of film density is possible if sample thickness is known. Near surface crystallinity of sample can be determined by the channeling of ions to analyze for lattice damage. This is how an RBS spectrum mostly looks like. Here, the relative concentration can be determined from the peak heights. Compositional depth profile can be determined from the position of the peaks in the RBS spectrum. To conclude with, Rutherford backscattering spectrometry is a powerful quantitative method in the scientific world. Thank you.
So what are the limitations for RBS? Well, first, there's a low sensitivity for light elements. Similarly to particle-induced X-ray emissions, RBS setups have little to no sensitivity for elements lighter than neon. This is due to the low energy X-ray attenuation in the X-ray detector window. Secondly, due to statistical fluctuations in energy transfer to electrons and photons, and in and annihilation of electron-hole pairs, RBS has a limited energy resolution at about 10 to 20 keV. Third, this technique gives information based on shape, size, and orientation of structures. It does not provide any chemical bonding information. This may be considered a disadvantage in comparison to other methods like XBS. However, the ion scattering technique used through RBS provides valuable quantitative information for large-scale structures from 10 angstrom to several thousands of angstroms. Lastly, since depth resolution is limited to about 10 nanometers, the RBS cannot analyze ultra-thin films.
So what is the resolution of this technique? The lateral resolution is not very high. We're only getting about 1 millimeter in the sensitivity of the lateral resolution, but the depth resolution is better, about 20 nanometer resolution. It also has a detection limit about 1 atomic percent of the element that you're looking at, and in the element detection range of helium to uranium, because hydrogen is too light for this technique. So the signal origins, we look at the Rutherford model, coming from the Rutherford gold foil experiment, where they bombarded a thin gold foil with alpha particles, which are just helium ions, and some of them were backscattered. And this was happening because of this Coulombic force as they approached the nucleus of the gold atoms. And so those backscattered ions are what the signal is that we're actually looking at for this technique. And so for that, the signal is going to change based on the element and the depth of the sample. So as your ion comes in and is deflected right off the surface, it has a higher energy, and as it goes through, it loses energy as it goes through the sample this way and loses more energy this way, so you end up with a lower energy when it reaches the detector, when it's deflected off the back surface and in between for the middle part of the sample. And then the graph here shows our signal with different elements that show, as it's a heavier element, you get a higher energy because of the atomic weight corresponding to the number of protons, means that there's a higher Coulombic force, which means there's a higher energy of the scattered ion. And this also shows the peak will broaden as your sample gets thicker, because you're getting the signal off the front and through the whole thickness of the sample. So the energy will be lower from the backside of the sample, which just broadens the peak. The front side of the peak will remain the same because that's off the surface atoms. So the scattering energy then goes down with the less heavy elements as well. Here are the references for this section. Thank you.
Some applications of RBS include analysis of composition, contamination levels of samples, characterization of the colloidal nanocrystals to quantify compositional changes during cation exchange reactions, determination of thickness density product of both silicate layers and adjacent film. Example of RBS on the nanoscale is this evaluation of lattice displacement in Mg implanted GAN by using RBS. In this experiment, they had a 3 millimeter thick GAN signal crystal grow by metal-organic vapor phase. And they tried to implant magnesium ions, but when they did, they could only go up to 50 nanometers of depth. so a lot of the magnesium remained near the surface. They used RBS with a 1.5 MeVH plus beam, and the H ions were detected with a solid-state detector at 150 degrees. The image to your right shows a spectra from the RBS of unimplanted and as implanted GAN from the 001 direction. The displacement concentration of the GA and N atoms was observed by RBS, which suggested that the intertales were introduced by the magnesium ions implanted in the GAN. The 400 nanometer emission was due to some donors and some acceptor pairs. It was also suggested that the origin of the high resistivity once the magnesium ions were implanted is affected due to the deep level of non-reactive centers.